Good morning, everyone. I would like to welcome you to the second week of this environmental impact assessment course. Like discussed last week, the first week was more about the theoretical concepts, about the tools, and about the process of an environmental impact assessment. And we had 2 days of lectures about the theory about the environmental impact assessment. And then in the last day, we also discussed some examples of environmental impact assessments. And so today's week, the second week of this course, we're going to go a bit more into the praxis, and we will have today a lecture on life cycle assessment by Kevin Dillman. And then the remaining of the week will be led by the Metropolia University from Finland, from our colleagues from Finland, where we'll have exciting examples of circular economy and sustainable development from Finland. I would like to present our speaker today. Our speaker today is Kevin Dillman. He's a PhD student about to finish his doctoral thesis about using life cycle analysis to assess the environmental impacts of different products. He will go more in detail of his work during his lecture, but he's also employed at the Sustainability Institute and Forum, where we work together on hydrogen production and the life cycle analysis of hydrogen production at different locations in Europe. He's writing his PhD thesis at the University of Iceland, and he's also working for Our Nature, the energy company in Reykjavik, which is a sister company of Reykjavik Energy. He can say a few more details about this as well. I want to very shortly outline the collaboration with Kevin. So we have this H2 cup storage project. In principle, it's a European project where we work together with colleagues from Belgium, Denmark, Norway, and of course, Iceland. It's a 3-year project that goes from 2020 until 2022. It's sponsored partly through the Nordic Energy Research Fund, partly through the Horizon. Different partners get funding from their regional funding agencies. The main objective of our project is to look at carbon-free or low-carbon fuel production. And one way of producing fuel would, of course, be hydrogen, which could be a substitute of fossil-based fuels, especially if it's done with renewable energies like wind power, photovoltaic power, geothermal power, or hydropower, as is the case in Iceland. Within this project, we're going to look at the different tools we looked at last week, like life cycle analysis. Kevin will go more into detail, stakeholder analysis, and economic feasibility. The 3 locations we're looking at in this project is Mortsel, Nivelles, and Hellisheiði. Hellisheiði is in Iceland. The other 2 are located in Belgium. Here, a short overview of the other employers of Kevin Dillman. Reykjavik Energy and Our Nature are 2 sister companies that provide most of the electricity for the Reykjavik area, but I'm not going to too much go into detail because Kevin might present this more in detail. I just want to point out the 2 main geothermal power plants that are operated by Reykjavik Energy is Neslavellavirkjun and Hellisheiðarvirkjun, which are located about I guess this must be somehow, yeah, okay, if you drive all the way, then it's 90 kilometers, but it's roughly straight distance 20 kilometers from Reykjavik to Hellisheiði. And as you can see here on the Google map, Google calculated the entire distance if you would drive to both power plants, as indicated here. Here are 2 aerial pictures. And so just to present also to Kevin what we have been doing last week, all students started to work on an environmental impact assessment project that they would like to work on. They chose a topic together. They're grouped in teams of up to 6 students. And one project will focus on sustainable palm oil production in Brazil. A second group will look at geothermal power plant in Reykjanes Peninsula. And the third group of students will look at a wind farm in northeastern Iceland. The fourth group of students will look at Vaxa, a company producing vegetables in Iceland. And then another group of students will look at the environmental impacts of the COVID pandemic how this would how this affected the carbon footprint and how this affected the environmental footprint in Iceland in particular. And then the last group of students will look at compare vegan diets with carnivore diets and with vegetarian diets, and look at the total environmental impacts. What happens if you shift towards it, if you shift your diet towards something that is more vegetarian or even vegan. So I think if there are no questions, then I would just give the floor to Kevin. Are there any questions? If not, then I would just ask Kevin to maybe introduce yourself more in detail and then start with your lecture.
Great. Well, thank you so much for that introduction. And those projects look super interesting. So it'll be exciting to see what comes out of it. I'm going to share my screen now to get the presentation up. And well, it's a pleasure to present to you guys today. Of course, unfortunately, because of COVID, we're doing this electronically and not in person. So, like, of course, I can't see anyone. So if you have any questions, just feel free to jump into the chat, like, and write it in, or even just to, unmute your microphone and jump in with a question at any time, and it's no problem. Because of course, it's a 2-hour lecture, but it's always, kind of more exciting if it's a conversation and there's questions being asked about it than just talking to a screen. So let's just get into it. And as David said, we'll talk about LCA, and I'm going to give you guys some industry case studies, both from my work as well as work that's been done at Orka Naturrunner and Reykjavik Energy. And just to give you a little bit of a background is, as David was suggesting, I'm an environmental analyst at Reykjavik Energy. And then as well, I did my master's, maybe similar to many of you, the way that you're doing your master's right now at the University of Reykjavik. I did mine at the University of Iceland and their Environment and Natural Resource program. And that's actually right now that I'm doing my PhD as a mix between the Civil and Environmental Engineering department and the Environment and Natural Resource department. I've actually just 2 works are officially published, and then I have one more that's accepted for publication coming through. So that's like most of my way being done through a PhD. And this review and meta-analysis of EVs, this was like doing a review of over 20 plus LCA literatures, and then I wrote an article about it, which I'm going to describe some of the results a bit more while we're talking. And then we later used these results from this LCA review to develop decarbonization scenarios for Reykjavik's passenger transport sector. And, I'm going to give some small details around that as well. So you'll kind of see how I've used LCA professionally, as well as how I've used it in academic work as well. And, and I'm sure David is full of examples as well. So it sounded like maybe you guys already had a bit of a background within LCA, but, I'll just like quickly kind of go through it. But what is LCA? I mean, it's an application of life cycle thinking. You basically want to consider the cradle to grave impacts. Of course, you will at times not be going grave to grave. You can go cradle to cradle or kind of within each of these circles. But essentially what you want to do is it helps avoid narrow environmental thinking, and it really gets you to try to focus on the hotspots or identify the locations that are actually leading the environmental impact and do it scientifically. And, kind of connect it all the way down the line to raw material extraction, to manufacturing, to distribution, and depending on the product, there's so many different products and ways that they're made, and the carbon intensity within the different kind of phases of a life cycle, that's the reason that you want to do it. You can additionally do LCA is factors, but other common life cycle thinkings is life cycle costing and a social life cycle assessment, which is kind of like a newer form of LCA. But if you think about it, these are, of course, the 3 pillars of sustainable development. And then, so you can be thinking about this in many ways, and we're obviously taking a look at the environmental kind of aspect of it. So I'll tell you what LCA is versus what it's not. Sometimes people might get confused between like a company-wide carbon accounting and the carbon footprinting. But it's not exactly the same thing. So maybe where a company-wide footprint would be looking across the business and like looking horizontally at what an entire business does and their fuel use within the company, their different processes, electricity use and like taking business flights. That's not exactly, the point of doing a product LCA. When you're looking at a product LCA, what you're instead is looking vertically and looking at the material that's being extracted, the processing of it, and the use phase of the product, and then of course the end of life. So just to give you a little bit of perspective of what it is versus what it is not. And so essentially, why is it useful? Well, then you're essentially looking at, because then you can ask the questions of sometimes, you might be wondering if Cronon is replacing plastic bags with paper bags. But is it actually better? I mean, and this has been a discussion that, I've seen a YouTube video about where they're describing it. When I first learned about LCA, that helped give me a good perspective, was that if you need to make the paper bag 3 times as thick, is it as good as the plastic bag? And so basically this is the type of thinking that is why LCA is an important factor. And so to give you some backgrounds of how it was started and what it is it's an ISO standardized methodology. And so ISO is like the International Standards Organization. And they put out 2 reports, and I mean, they were the ones who kind of formalized it. And essentially they give you an exact definition of how you should fill out an LCA report. And this is like the definition of how to do a life cycle assessment. Although now at this stage, there's many variations in an academic one versus an ISO standard, and we can go through all of that. But essentially it began in the 1960s due to concerns over images and raw materials. And one of the first people to look at it was actually Coca-Cola. So exactly like I was just suggesting with the plastic bags, well, is an aluminum can better than the glass bottle? And then you have to think, okay, well, what about how it's recycled? And I guess if you're having a lecture on the circular economy, you guys are going to talk a lot more about that. And then so basically, okay, well, what about how it's made? And what about aluminum? I mean, taking one step back, and the electricity and all the energy that's needed to produce aluminum, as we're pretty familiar here with in Iceland, versus glass. And so just considering these different impacts. And that's what LCA will measure, the environmental impact. And while many people might often just think of it being in greenhouse gas emissions, it's actually, quite many things that come out of LCA. So I'm going to go through it in the next steps, but basically you'll see global warming is just one of the midpoints and categories that is being thought about. But you can also think about acidification, which is, can be happening both in the oceans as well on land, kind of local air pollution and political matter impacts to, human toxicity. So, it looks at all these kind of midpoint categories of what is coming out of the process. And then you can see the damage here. And this is essentially suggesting, okay, when you group all of these things together, how bad is how is that affecting human health, ecosystem quality, climate change, and extraction of resources when you're looking at, fossil fuel or mineral extraction? And so this is a midpoint, and this is endpoint. I'll kind of describe that a bit more, but essentially there's 4 steps in an LCA. And so the first step is the goal and scope. Second one is gathering the life cycle inventory. Then you want the life cycle impact assessment. And then lastly, throughout the entire stage, you want to be interpreting the results, because often a goal and scope is what's going to help you define your boundaries and what type of work you want to do. And life cycle inventory, you want to be conscious of everything that you're including. And in the impact, you want to make sure that's being interpreted correctly. And then also when you're producing a report or whatever format that you're giving it out in, you want to give an accurate representation of the results. So within the goal and scope, the goal of an LCA should basically unambiguously state the intended application. And this is really important because, there's a much bigger difference between maybe doing something for on power, and if they want an LCA completed in order to have the carbon footprint of their electricity production to be competitive in the market, well, then you want to understand exactly why this LCA is being done and realize what's the important factor. And you should probably be taking, a heavy examination on things that might have a high impact on climate change, but maybe in terms of water use, maybe that's not a good example, but maybe some of the other impacts that I was just showing, that you want to focus then on all the materials and all the carbon intensive things that are quite important, when maybe some of the other aspects that might be important and other considerations, having the goal and scope helps you really like focus on where you are. And when you're getting the scope, you want to look at what is the functional unit. And the functional unit is essentially saying within that system, what are you truly trying to measure it by? So what are you dividing by? Is it the like global warming potential per kilowatt hour? Is it per, like looking at a plastic bag? Is the point of it just the bag, or is it how many uses out of the bag? Or another example is for a vehicle, is that oftentimes the functional unit, you might just think like, okay, well, it's just to have a car, but a car is not like the end game of itself, but it's actually to travel 1 kilometer. So then it's, okay, what are all the environmental impacts over the other entire life period? But then you want to consider the lifetime and, well, how long is that car going to be driven? And if it's over 150,000 kilometers, well, then you're going to kind of measure it out throughout the entire system. Then as well, you want to see the product system, kind of like how far back do you want to go? I mean, do you want to stop? Or do you want to go all the way back to the resource extraction, or do you want to focus on a specific process and take a deeper look into that? So that's something to consider as well. And that falls into the system boundary, is kind of drawing the lines of how far and how wide to kind of make your assessment. And then you want to look at what type of impacts. So sometimes you can take an LCA analysis and, you're kind of, even though you should always be doing all of them, that you'll take a key focus on some of probably the impacts that are most important for the process that you're looking at. So this is an example of a product system where, you have your extraction of resources, transport, finance or raw material, transport again, manufacturing. And so basically, I mean, this is the life cycle perspective that we were giving, but now seeing it in a product system where you get like a good view into what it actually looks like. And then here you're drawing the boundary of what you are actually interested in looking at. And whenever you're describing an LCI or LCA, you normally have a unit process like this. And then, I mean, you can see that you have your inputs and your outputs, and this is how you begin to develop your LCI. And so this LCI, you have this inventory of inputs and outputs in a process system. And, this was done, David, can I ask you one thing?
Yes, of course. Yes, of course.
When you're seeing my screen, is there this chat window? Because I have on my screen, like, do you see the full screen?
No,
or
we
do you
don't see your
Zoom?
chat windows. We only see yours, at least I only see your slides.
Okay, because it was, yeah, great. Just because it was like blocking a little bit, so I just wanted to make sure that it was.
But of course,
presented.
every student can arrange this themselves. So if they have the chat window open, then they might, everybody has to arrange the screen for themselves.
Okay, perfect. That sounds good. I just wanted to make sure that I wasn't like talking about something that was covered.
Yep.
So, okay, great. So yeah, this is the life cycle inventory. And then you can see here that you have your inputs and your outputs, and the key factors that you want to look at are the material inputs and the resource flows, both in and out, the use of energy, and the emissions that could be coming from the process itself, or, other parts, whatever you want to consider. And then, so this is like, for one example, this is like from alumina refining for a project that I was working on with aluminum. And you can see you're looking at like the inputs of water, the use of oil and electricity, as well the outputs of the process, that they have carbon dioxide that's being emitted, particulates, and also water discharge. And you want to basically have like a mass flow and energy flow and water flow that's coming in and out of each individual process. And as you shape these all together, as was shown before, that's what's going to develop your LCA. So then once you look at the LCIA, then you can begin to look at what the impacts are across when I was showing you this toxicity, land use, other factors, then you can see, and this is from like a famous, widely cited vehicle LCA. And then, you can even break it down by component. And then, for example, of global warming potential, where one of these, you would see like grams of CO2 or tons of CO2. And then you can even have it broken down by each process in which you're included. And then so you can see like, okay, which, which component is, you begin to do a hotspot analysis. And then you can, and then when we're talking about this LCIA kind of interpretations, then as you bring it all together, and for example, you have this like global warming potential, and then you have different examples like here for different vehicles, and then you can see like this is the use phase. The fuel and electricity is what's causing, like a base of a lot of the emissions. You have the production of the vehicle. And then for EVs, you see that the batteries have an additional emissions. So it's basically, and that's just for global warming potential. And then you can do it all the way down the list of basically these different impact categories. And this is what, an LCIA would look like. And then you can go into the interpretations of the results. And then this is where, you try to identify like significant issues in the product system. You want to take into consideration the sensitivity and the consistency of your work. And then you also want to talk about any limitations within your study that maybe it was difficult to get data, or there were certain things that you weren't able to do, as well as recommend, okay, what is the next step? So if you can basically interpret, if we're looking at, the carbon footprint of a road, then you can see that most of the emissions are within the construction and the operation and maintenance. But then you can see like specifically within this that there's like one specific portion that's causing quite a lot of the emissions. And then this is where you can identify certain things where maybe here, if there's a way where you can reduce the footprint of this process, then maybe you can, to a great extent, reduce the footprint of the road, where maybe without such an LCA, you might think that, oh, well, disposal was a big portion or something. But then maybe that 4%, and even if you reduce the emissions on that, you're not really like tackling the bigger issue essentially. So this is a way to like review and try to interpret, what you're working with. So I'll give you just a quick talk about the LCA methods, because there are a bit of slight differences. There's a process LCA, an input-output LCA, and then a hybrid LCA, which is like a mix of these two. And to understand what the advantages of each are, is that this PLCI, or process LCI, LCA, is that you have much higher data reliability, and you're getting specific and detailed data sources on a specific process, and you have low uncertainty, versus a economic input output. It looks at all the imports and exports of a country, and also what's being produced in it using large data sets. And then but what it allows though is it takes into consideration, because for example, the agriculture, like how do I say this, like the agriculture agriculture as a whole then buys a lot of machinery. And then so a process LCA might just attach, okay, well, the emissions from that machinery. But then the whole machinery industry, which is supplying agriculture, has a whole set of emissions. So this is called a the truncation of, okay, well, all the machinery needs all of these inputs. And then you go down like one more level, okay, what about the metals? And the metals, but then the metals need agriculture at one point. And, it kind of goes down this endless list. What input output allows you to do is kind of take all of these emissions into consideration through it's like a series formula. If you guys remember like math, like deep mathematics. But essentially what it does is it allows you to truncate and take all the emissions over the entire kind of spectrum of what is included. But the problem is because it's at the kind of country level, you're often just stuck with like 26 categories, or with better databases can be up to 400 categories. But still, this is kind of like a low visibility and like granularity, as opposed to a process LCA where you're getting very specific data on that process. So I know that's a bit confusing, and it's a bit difficult to explain, but if you have any questions, I'll be happy to explain more. Yeah, and then so you can see that there's obviously limitations to both, and these economic input output LCAs work, the data is already mostly available for whatever you're working in, versus a process LCA, you have to collect the data and gather each individual unique kind of process within that. So that's just something to think about. What a hybrid does is try to combine these, where you'll maybe do a process LCA for some of what you're working with, and then connect an input output LCA on top of it. So, and then you can also review LCAs, and this is what I did in my studies. So it's basically you want to use existing literature to form an overall like kind of consensus from all the research. And then you can do a meta-analysis, which is, you know, kind of analysis taking all this, or review maybe how the methodologies were and how they differed. And I mean, you can see here, this was from the work that I had actually done. And it was looking at all, you know, looking at one study, another study, and, you know, down to like over 20 studies, and gathering all the results, how they did it, and trying to gain a deeper understanding of, should the process be improved? Is there something that, you know, like scientists could be doing better? You know, you can give basically input to a lot of these things, as well as extract the results and try to gain some sort of consensus out of it. So that's kind of the first case study that we're going to give you. And this is a case study on a review of electric vehicles, which is the work that I did, and talk to you a little bit about LCA for EVs, as well as like a uncertainty. Oh, sorry, that's in there twice. But yeah, just to give you a little bit of a background as well, like this work, and to show the value of LCA, kind of the work that was done ended up being given to the Minister for the Environment and Natural Resources from the CEO of On Power. So it just kind of shows that, you know, hopefully if you do work that's applicable, you know, oftentimes it can lead its way into policy, and hopefully it should be guiding policy, because you're taking like a much deeper look at the carbon footprint. And so, and then, you know, you can kind of give the reason for why policy should be supported, such as the movement towards EVs. So just to give you background, obviously emissions in Iceland, I'm sure you guys are getting quite familiar with the, you know, low emissions that come, you know, from the energy sector. But then when you zoom in, but the energy sector is still, you know, I guess like 35, 40% of the emissions. And when you zoom in, this is just on the energy sector, where most countries might see that the energy industries are causing quite a lot of the emissions. That's not as true here, where it's actually rather, you know, the transport industry, which is the leading use of emissions with the energy sector. So this is where you might end up getting like having quite a debate on electric vehicles versus combustion vehicles. If we were in person, I'd probably like drive a little bit of a conversation. Unfortunately, I know this isn't a great format for that, but you know that this is quite like a an opinionated topic, or many people often have the debate of whether they think EVs are better or not. And the reason why it's important to think about this as well, we know global deliveries of EVs are kind of going up exponentially. The Iceland has announced a new climate strategy, and this was EVs being percentage as like, and you know, it's important for us to be thinking about this, because where Norway is number one and Iceland is number two in terms of percentage of total vehicle sales, which are electric vehicles. So I mean, this shows that it's an important topic that, you know, we do want to know the environmental impact, and this is because and On is frequently receiving customer questions regarding the environmental concerns. And often they might be asking, well, aren't the batteries actually worse than combustion vehicles? And then what about the electricity required to power them? Doesn't that make them worse environmentally? And the reason it's important to answer these questions is because, for example, in Norway, where I just showed was like one of the leading countries in terms of EVs, you know, the biggest concern that they have is about lack of range, which is of course improving as, you know, battery processes are becoming more well known and researched and manufactured. The second one is that they don't actually believe that EVs are more environmentally friendly. And if this is a barrier towards implementing a solution where in Norway they also have 100% renewable energy, well, then that's a bit of a question of like, okay, well, if this is stopping them, then I mean, there should be kind of a scientific conclusion on this to overcome this barrier, essentially. So what does a vehicle life cycle look like? And I mean, normally I would like have a discussion and maybe talk about this on the board and try to get you guys to draw it or come up with it on your own. Um, but I can just kind of give you the results. And it looks something like this. Of course, you can go into much more detail on each one of these. Essentially, at the end of the day, it's like you can usually break down everything to kind of this kind of step. So you have your raw material, you have your production, you have the use phase, and you know, in the case of something that's using fuel like a vehicle, you want to think about the energy production that's going to go into it. And then lastly, the end of life. Of course, there could be transport all the way through in there, and many more details, but this is the overview. So when we take this more detailed look, when you're looking at a EV versus a combustion vehicle, many people talk about EVs as zero emission vehicles, but of course they're just talking about the tank to wheel, or essentially the driving of the vehicle. And then you can see, of course, in a combustion vehicle, you're combusting the fuel, you have CO2 emissions. With an EV, there's no combustion, you just have the energy stored within the battery, and you're driving, it's turning the drivetrain is electric, and so you have no CO2 emissions. But when you go backwards and then you look at the well to tank, so basically, well, how are you fueling that car or charging that car? Well, then of course there's still CO2 emissions within the power generation, CO2 emissions within oil refinery, and then of course taking a step back is the extraction. I mean, in Iceland, it's a bit different in terms of that. This fuel extraction might actually be for electricity, from hydropower or from geothermal. But in most places, that you would extract a fossil fuel and then burn a fossil fuel for power, and then go through and have your charging. And and with oil, it's kind of always going to be in that direction. So it's essentially looking at it from these two different perspectives. But of course, Iceland and much of Europe, and why we want to move towards renewables is to kind of eliminate, hopefully, this CO2 and CO2. So there's complications with this. When first reviewing this this stretch of EV reports, is that there's a lack of consensus due to new technologies, and then system boundaries are often difficult to draw. And so this was from my first report, and like the results have updated, but I wanted to show this to kind of give a quick just overview of life cycle emissions to make it like obvious. When you're just looking at the production and the use phase, which are the kind of larger like the biggest portions of emissions. Well, with EVs in Iceland, you can imagine that the production emissions to produce an EV, which we were showing because of the battery pack, are often going to be higher when you're looking at tons of CO2 equivalents. You're reaching almost 10 in this example, where then here with diesel and gasoline, it's both sitting around 6. But then you see during the use phase that you have way more emissions, and in Iceland, where it would be clean, it would be much less. And so the final results of this first report was essentially saying that it's like 4 to 4.5 times emission more the EVs in the vehicle. And this initial production emissions is important to look at, because as you can see, the EVs are starting here, and your diesel and gasoline comparison would be like starting here. And then as you go up, but then the use phase of the vehicle in Iceland, because it's clean, it would look something like this. In the EU, it'd be higher, but not as high as the US versus natural gas, versus if you're, basically powering your EV using coal, you might never even like reach an environmental break even with some of the other vehicles. And when you think about battery capacity, this isn't ultra scientific. Like this isn't coming from my published report. This was coming from like kind of a first initial screening that was done. So I just wanted to do this to kind of show an example, is that, you might consider like a 24 kilowatt hour like Nissan Leaf. But if you look at a Tesla with a huge 85 kilowatt hour battery and move it up, well, now suddenly, if you think about the emissions in that sense, even just by doing this, even in a very clean electricity sector, it still might take 60,000 kilometers before you reach this environmental break-even point. And then when you look at these different electricity sources, like we were showing, well, now if you started at this higher point and have a high greenhouse gas intensity factor in the electrical grid, well, then, it could be well into the 100,000 kilometer mark before you reach this break even. So then this is where you want to start thinking about, like, even if it's the right solution within certain context, it may not be the right solution. And that's essentially how we want to think about. Of course,
excuse me, can I interrupt first?
Yeah, sure, please.
I was just thinking about, you had like sort of the different sort of style and ranges and size of the electric motors, but about the gasoline and diesels, you only have just one average, one mean. So could you just like in 2 sentences, how did you come up with the values for these? Are it like just sort of sedan, or is it like a mean from sort of trucks and cars?
Mhm. Yeah, so this definitely we were only looking at like sedans and basic vehicles. Of course, like but there is a difference between a luxury vehicle like a Tesla and comparing that to, like a Yaris or something like that. So I mean that's a totally fair aspect, in which why I put like a little bit of an asterisk that this wasn't like wholly scientific. This was like kind of like a report, like of a first kind of like screening of the work being done. But we did, go into research and basically find like, I mean, this was like a BMW, I think a BMW like example for both. But at the end of the day, like the sizing of the kilowatt hours per battery was, we just purely like scaled up. If we have this many emissions per kilowatt hour, if you go up further, like, and use that same amount of emissions per kilowatt hour of battery, because of course then you need a larger battery, this would go up. But of course this is like, not as scientific as it could be. And in the further results, like I'll show that a bit more.
Okay.
But at the end of the day, yeah, it's just looking at sedan. But this was just trying to like paint the picture of, if you think about like a vehicle that's requiring more production emissions, well then you're really going to need to pay off more in the use phase, essentially.
Yeah, thanks.
Yeah, no problem. Thank you for the question. And then, so if we look at this over time, of course, the EU electricity mix is kind of decreasing, and the US electricity mix is also decreasing. So if you think about it over time, it is likely that, you'll see this bend over time as more and more renewables are added into the electricity grid. And so this is something we want to think about. All right, so now this is like, that was the report that I'd done before, which was not peer reviewed and was just like kind of reviewing 2 articles. This then turned into, I started working with the University of Iceland. It actually ended up turning into my PhD, was to look at these aspects and now do this over 20 and kind of give this exact concept that I was kind of showing with this higher and lower production emissions with an EV. And now this is just like hypothetical. This isn't trying to put any numbers on it. So it's exactly that. And then if you apply, we like just 3 imaginary electricity mixes. I mean, you can kind of see that this is like the general shape of what it would look like. And then these are the different break-even points. So it's basically suggesting, like if you have an EV with low production emissions and a low use phase emissions, you're going to reach your environmental break-even point the fastest with a compared like a combustion vehicle comparator, uh, the fastest. And of course, the dirtier that is, the sooner you'll reach this environmental break-even point. So like each one of these intersections, like from here on out, well, now the EV is actually leading to an increasingly like less amount of emissions than the compared combustion vehicle. And then of course, where you end is like you can assume that a vehicle lifetime could be 150,000 or 200,000 kilometers. And according to that, if you're, say we're here in Iceland or something, then I mean, you're either, this gap is how many emissions essentially you saved by driving an EV, and the longer the lifetime, the longer, like the bigger that gap is because of this longer use phase, essentially. And so when you're looking at this, when you look at a lifetime, you think of a lifetime in kilometers traveled, so in distance. And so what we did then for my paper where we reviewed the 20 studies was essentially we did this for all of Europe. And we kind of looked at like in each country, and we took like a crossover 20 studies, and we did it with a average and with a standard deviation, and essentially looking at like, okay, how many kilometers would you need to drive to environmentally break even in that country? And so the diesel case is probably the more interesting one, because that's the one where the kind of like diesel you can imagine is this one where the EVs get into more range of potentially not being more environmentally friendly. And you can see here that in diesel case, still it would just take 30, like, it's on average, it would take 34,000 kilometers for an EV to break even within Iceland. But then, when you look at, and it is a very good question, where this is not including SUVs, and this is not including trucks, and we're also not looking at hybrid vehicles. This is just purely for pure battery electric vehicles, sedan style cars versus sedan style diesel comparators. Yeah, and so to make that like a clear distinction. And but then if you look at the UK, where their electricity sector is not as clean, I mean, you can see that it's going to take 244,000 kilometers to break even. And where many of the studies considered the lifetime of a vehicle to be 150,000 or 200,000 kilometers, I mean, you're essentially saying that EVs are actually not leading to less greenhouse gas emissions. So when they're being implemented as a solution, you do want to take this into consideration. And then when you go to a country maybe such as Poland, where they're using a lot of coal production within their electricity mix, and also within Latvia and Estonia, I mean, you have these same issues. And Malta is in this as well, even though you can't see it here. It's actually highlighted in yellow because they actually will never break even, because their electricity grid is, is with enough greenhouse gas emissions that it would kind of never lead to this break even point. And so what we're showing here is then, like I suggested, we took the statistics of the average from all the research that we did on EV sedans and combustion vehicle sedans, and using the average and the standard deviation, we did a Monte Carlo analysis, where essentially you then run, in this case it was 200,000 simulations, and saying, okay, within this range of averages, so that way it's not just taking one average, you're looking at the entire field of like statistics essentially. And then we map that on each, every 10, kind of every 10 steps of electrical grid greenhouse gas intensity. And then you can kind of see how that played out, where essentially you have like a probability curve of here on the low end of electrical grid greenhouse gas intensities. It's just almost 100% certain that it's going to go well. So Iceland and Norway, who are, quite right next to each other, you'll see right here that it's basically suggesting that it's 100% EVs are going to be better. And that probability begins to drop as you have higher and higher electrical grid greenhouse gas intensity. So as you go into Austria, which is still clean and is still seeing, quite a very high probability of EVs performing better, to the EU average, I mean, you go down to the UK, then as you go to Greece, I mean, you start to see that, there's a 90% chance that, EVs are better than petrol, but, maybe just a 50% probability that an EV you would see on the road is actually better in terms of lifetime greenhouse gas emissions. And then you can see all the way in Latvia, now you're starting to hit like really low probabilities. And so this is what you want to avoid. And the reason and then you'll see here, how we mapped it, and with Latvia being the lowest, that's why it was on the map. But then Malta is the second lowest, and there's a reason I'm going to be bringing this up. And then you can kind of see that we just kind of put like blocks on this by probability. So that way you can kind of just see like all the countries at once of what the probability looks like. So then from a policy perspective, like why is this important? And this is like the value of what LCA work can be and what it is done, is that for the diesel example, like we were just talking about, this is talking about like the final greenhouse gas emissions. Like does an EV, like in Iceland, an EV would save you 20 tons of emissions within this example, compared to a diesel counterpart, where Malta and like EVs would actually lead to 12.5 more tons than the compared counterpart. But then the reason that this is important and why our paper was able to provide like some policy advice is that then when you look at the difference of these two island nations, Malta has an electrical grid of 1,000 grams CO2 kilowatt hours, but they have the policies to remove registration ownership taxes, subsidies for VAT, incentives for EV charging infrastructure, exactly the same as Iceland's pretty much. So it's like they're implementing the same policies, but the results of what's happening, I mean, when you look at the electrical grids, I mean, it's almost 50 times worse to use like, in the electrical grid. So you can imagine what that means for the electric vehicle. And I mean, that's what the map is showing. And then, so it's basically suggesting like, if you have the same policies, one having almost 50 times more greenhouse gas emissions per kilowatt hour, there should basically be some questions of how scientific and research can help, kind of fuel policy debates and like, try to help countries consider if they're, kind of implementing the correct solution for, if you're suggesting that this is being implemented as a green, like a global warming potential policy, well then, I mean, it should be supported by the science, essentially. This came from my original report. This wasn't within the scientific publication, but it's also interesting that, you know, when you look at different factors as well, is that, you know, particular, like you can think about local impacts as well. And, you know, particulate matter is, of course, a form of local air pollution. It's like but like particulates that are less than 10 or 2.5. There's different categories of it. It's PM10 or PM2.5 microns in size, essentially. And in 2018, for example, over just a 3-month period, you know, there was over 10 plus 24-hour periods in which the levels passed like the WHO limit of 50 micrograms per meter cubed of particulate matter. And this can lead to coughing, asthma attacks, bronchitis. And so, yeah, you can see on just like a random day, I just went online, and this is like a bit older now, but I mean, it's been still just quite the case, is that if you look it up, local air pollution, you know, on a random day I looked, we were over the WHO safe guidelines. And then, you know, they estimate that there was a 65 annual deaths from air pollution in Iceland, and you can only imagine what that would be in other places. And also then when we were talking about social impacts, I mean, I'm just including this because it's interesting around EVs, but, you know, we don't have to, like, it's not too much related to LCA, although there could be social LCAs, of course. But for example, within lithium and cobalt mining, you know, Democratic Republic of Congo supplies 55% of global cobalt. You know, 20% of these operations were identified as having used unethical child labor practices, and Amnesty International found a high level of exploitation with the cobalt supply chain. And this is essentially the cobalt supply chain. And, you know, many of the companies that like people are quite familiar with are, you know, kind of also existing within the supply chain. And Amnesty International kind of wrote about them and kind of suggested, and then asked Apple, Samsung, VW, and a lot of them basically suggested, yeah, we're looking into this, but that they're currently evaluating, or you know, Samsung kind of suggesting like, oh, well, it's very hard to chase where it's from, so, you know, we can't really determine if it comes from there or not. And then you know, like and the VW, you know, to the best of our knowledge, it doesn't come from this, but, you know, it kind of shows that, you know, when it comes to social factors, this is, and especially purchasing and supply chains, this is something that's becoming increasingly aware and important in people's mind. And for example, the palm oil, I mean, that's probably going to be something that's quite something that's looking at it from this perspective as well. So just to kind of review social impacts, but this is, as I said, this is kind of unrelated, but just interesting, is basically suggesting that it's like at all levels where things are being failed, which was suggested by this report. It's like the Democratic Republic of Congo isn't protecting its people or its obligation to human rights. Companies need to undertake like heavier due diligence to meet international standards. And probably we need to question like electronic and EV producing like, and kind of force them to be more transparent in their purchases. And the more pressure we put on the companies, the more companies will put that pressure on countries and their suppliers to kind of be ethical. So there's, you know, some social factors to think about that. And while I've never done a social life cycle assessment, I think that it would be quite interesting. We're at like 50 minutes. David, should we maybe take a break for 5 minutes, or?
Yeah, I think it's good to make a short break. Maybe if I just may make a comment to your first case study, which is really a nice case study, and thank you very much for presenting it. I pasted in the chat this calculator pse.ch link, which is from our colleagues from Switzerland, from ETH Zurich. PSE is a research institute at ETH University in Zurich. And this is a little bit what we would like to do within this hydrogen project, to look into maybe different fuels, comparing electric cars also with hydrogen cars, and also looking at the different types of cars. So this would be kind of the next step to complement what Kevin, the nice overview that Kevin already presented, and where we might look into the future. So you might look what the Swiss already did for the different individual cars. The question came up, you know, if you compare a SUV with a small car, So that's what they did within this huge database where they looked at different cars. And also what they took into account is the shift of many countries are shifting towards renewables. For example, Austria by 2030, they will have 100% renewable electricity production. So they will gradually shift towards a lower carbon footprint in the electricity grid. And this will, of course, then also affect the policies towards electric mobility. So it's a kind of a dynamic system, which we might be able to take a closer look into. It's just one thing I wanted to comment on. If there are any questions, please feel free to do, and then we might make a short break. Kevin, it's up to you really to assess how long you want to make the break.
Yeah, sure.
I have one question.
Yeah.
About the if EVs or electric, like fossil fuel cars are better. When they're doing this analysis, are they considering all the energy and the things you need for making the fossil fuels into like viable products to use in your cars? For example, you have to like refine the oil and ship it around the world. Do they consider all these things when they're like doing the final like polluting measures on the fossil fuel cars, or is it just like the pollution from the exhaust?
No, so they definitely they definitely go into like you're suggesting, you know, and even including like the transportation to get the fuel to places, but also you're saying like the refining to get them into the oil products that's needed, as well as like the machinery that goes into it. Often when you're doing LCA, and perhaps I could have described this a bit more, is you're often also pooling from like databases, which come from EcoInvent or other, which is Swiss as well. Or these other like kind of large databases, and they will like take published research and develop like databases that have data on this, because of course it'd be difficult for every researcher to like come up with their own conclusions about all the way the refining process like way back. But what you do is they have databases that suggest if you're buying oil from the US or from Europe or from here, that all the impacts, like they've done the research to do that. So that way you can focus on your product system and then plug in like the data that they've generated into your model. So that way you can have this. And so they're called like LCA databases. And then this is how you kind of like take these downstream things, which would be kind of difficult for you to do at this large system level, and then use that data in order to build your product system.
Great, thanks.
Yeah, no problem. So with that in mind, I mean, maybe, like we can just take a 7-minute break since hopefully, we're just sitting at the computers. Let's hopefully that we can just start back up at 11.
Sounds good. Let's meet at 11 o'clock.
Alrighty. Well,
Yeah, Kevin, I think you can just go ahead as soon as you feel like it.
yeah, sure. Great. I wasn't sure if
Yeah.
my microphone is still working. Okay,
Yes.
perfect. Okay, in that case, so we're just going to go through a few more case studies in this next 50 minutes. And so this one is looking at geothermal energy production at Helliseiði. I mean, so this one is coming now from more of the on-power side, and work's done from Martha Ross, who is the managing director at On Power, and as well as a PhD student at the University of Iceland, where she's published an LCA study on the geothermal power plant. So why LCA for geothermal is, of course, geothermal energy is an important energy resource in Iceland. There's very few published studies on geothermal utilization, and they're often focused on low temperature geothermal power plants. And with the directive that renewable energy should be expanded, and the primary energy factor, renewable and non-renewable, and per energy carrier is becoming compulsory. It's becoming increasingly important to perform LCAs. So just to give a little background on Helliseiði, it's of course a combined heat and power plant. It's in the Helliseiði in the Hengel area, and then basically that's where, when you're driving to Kerrigarði and you ever see the big steam plumes, then of course to the left is the On Power power plant. So current electrical capacity is at 303 megawatts, and with 133 megawatts thermal, with a full capacity of 400 megawatts. And that's also where, a fair amount of the district heating and water that's coming in that heats your homes is also coming from this power plant. There's 47 boreholes, and I think now there's even more. I think it's probably around 55, and it's about 20 kilometers from Reykjavik. This gives you a good kind of background of the process, and if you've ever been to the facility, this is a bit what it looks like. And I'm not necessarily going to walk you through each step of the process, but if you know how a double flash power plant works, then it's basically under this setup. So to give you kind of a better, from an LCA perspective, is that this is exactly when we were talking about the materials and the fuels and construction, is that, of course, if you're doing an LCA for a geothermal power plant, you don't necessarily have the time to go and research, well, how does the steel industry make steel and all that, but that's where you take from background processes. So this is what's going to come out of the databases that I was suggesting. And then as you're constructing the wells, you see, okay, well, how much steel do I use? How much concrete do I use? How much plastic do I use? And you look at all of these, and and according to, often you're taking design documents and even purchasing bills and everything. So how many, oftentimes you'll just know how many meters of pipe that you need within a geothermal well. And then you calculate, okay, well, what's the thickness of that pipe, and what's the material? And now what's the density of that material? And now suddenly you can start to get the quantity of the material that's being used within each one of these kind of processes, the collection pipelines, the power plant buildings that house all the machinery, then the heating station and the heating station machinery. And also then you can also add transport as a background process of getting all these materials to the plant. Then of course you're operating the plant, and the plant of which itself has emissions. And what does it take to maintain the plant, as well as the geothermal fluid, as I suggested, what emissions, and what is the chemistry of the geothermal fluid that can result in life cycle emissions. And then Martha didn't include end of life, and that's because, well, there hasn't been an end of life of the power plant. It's still in operation, so it'd be difficult to kind of measure this. And with knowledge of the industry, you can kind of know that a high percentage of the emissions are going to come from the construction and the operation, and quite likely 99%. So when you look at allocation, so this is something that needs to be considered heavily, especially when you have a multi-product system. And this is often within geothermal power plants, there's quite a few methods of how to allocate, because, you can kind of see it as okay, you build this entire huge power plant, but if the power plant was built for purely electricity, well, then what about is the heat just the byproduct that's coming, you know, in like heating our towns, or was the heat the initial product and electricity is the byproduct? And often it's difficult to determine. So Martha performed an allocation where she looked like there's some things which are shared, like the geothermal wells and the wellhead equipment and the geothermal fluid. And then there's other ones that are, you know, kind of stand on their own, basically that within the power plant buildings, the all the, you know, kind of electrical generators and stuff. Well, then that's like only on the electricity production side. And then on the hot water side, then you have any of the heat plants and any of the additional components that are focused on this. And so Martha performed like multiple allocation methods where she looked at multifunctional processes other than energy flow, geothermal fluid, and then as well looking at the primary product, electricity and heat, and then basically how it gets shared between these different kind of cases. So as you can see, when you're looking at the carbon footprint, you know, the carbon footprint for electricity is, you know, significantly higher than the heat. And then this is according to the different kind of allocation methods that I guess to how you apply it. You know, if you just look at energy produced, you know, they're right next to each other. If you look at heat, then, you know, it's like this. So it's that the allocation that you do like then impacts the results of whether it's being applied to the electricity or to the heat according to how you're doing this allocation. So when you're looking at the results, you have the LCIA data, and when you're getting the site-specific parameters for the scaling of the LCIA data, I mean, how do you kind of like collect it all? So it's like, okay, you look at the number of wells drilled, you're also looking at the total meters drilled in each individual well, and then you have, you know, maybe in headless area, it could be that you have, if it's about 2,000 meters per well and you have 50 wells, then you have, you know, about 10,000 meters of wells that have been drilled all around the site. And then also the length of the collection pipelines, if you've ever driven out there, like those igloo houses, those are each of the wellheads. And then you can see that some of them are quite far from the power plant. So then you need to, you know, kind of send the piping and the fluid back to the power plant to then produce the electricity and to produce the heating. And then, you know, you need to at minimum collect additional wells, the composition of geothermal fluid, the mass flow and energy content, the lifetime of the plant, and as well as the capacity factor. So there's a lot of different data points that if you're trying to do a large scale like LCA for example, this geothermal power plant, there's quite a lot of data that needs to be collected. And I've been working with Marta on this. When you do the LCIA, this is like what we were talking about before, is that, you know, within the construction phase, and I'm quite certain that this is looking at, this is like where does most of the, like in what phase does most of this material get used? So for example, diesel, of course it's a renewable energy plant. So it's during the drilling that almost all diesel is being used. But then if you look at, for example, the asphalt, then of course this is like within the like within the buildings themselves and asphalt and plastic. So you can see like this is where you can start to identify where different, you know, kind of components and materials are within each process. So Martha then published LCI, and she published a detailed inventory within the Journal of Life Cycle Assessment. And I mean, I've worked with Martha and as well as many people who are interested in the Hetless AD site because Martha published this report and has this data available. And so it shows the value of life cycle analysis because now on Power and Reykjavik Energy, I mean, we're in probably 5 different Horizon 2020 projects and grant agreements, because by having this LCA data, it becomes a very interesting site to then be able to basically consider what the environmental impacts are for geothermal, and it supports the research further. And because of this work, that there's been substantial changes to the operational parameters. I mean, for example, CarbFix has been implemented, which I would imagine that many of you are familiar with, but if not, this is the process in which because of the emissions that come, geothermal still has the emissions that come from the geothermal chemistry of the geothermal fluid. Carfix was put in place where basically they run the CO2, they have a capture plant that essentially runs the CO2 through water and captures it enough of the CO2 within like a liquid. And then they send it back down into the wells and send it back into the geothermal reservoir, where that CO2 mixes with the porous rock that we have here in Iceland. And then that CO2 then because of the chemistry will be solidified rather than being emitted into the atmosphere. And as well, that we also have the electrical drill rigs instead of diesel drill rigs, which now that we plug the drill straight into the power plant and use renewable electricity instead of using fuel. And this is big for climate change reasons. And then, so this shows essentially like that an LCA can change operations by identifying the hotspots in which, emissions are coming from. And this kind of shows that, also the chemistry of geothermal wells changes over time. Then let's say there was a much higher grams of CO2 and of H2S, and that over time, like the chemistry of the well itself begins to change. This is for Carfix and Solfix, and this is like increasingly like the amount of CO2 emissions before like 0% were being captured at Hetlaseyði, of course, and then CCS stands for carbon capture and storage. And increasingly, and it stayed at this point right now, around 33% of CO2 emissions are being captured, or then around 60% of the H2S emissions are being captured. And so this shows like the benefit of Carfix and Solfix. And then the drilling using electricity instead of diesel. So on average, around 150,000 liters of diesel was being used per well. And that would be like 160 years of driving a family vehicle. So this shows like how much diesel is being saved. And there's been a commitment from ON, and it's been in place for a few years now, that all wells in Hetlaseyði will be drilled using an electrical well, as well as for Nesjavellir. So when you look at the contributions of all these emissions, you can kind of see that like these are the impact categories, which we had discussed earlier. And so when it comes to global warming potential, you can see that the geothermal fluid, that's like the main, and essentially the emissions that come from the power plant are the, kind of main emissions that come from it, which is, essentially what to be expected. Let's see if there's any other, like acidification. That's maybe another interesting one, why it would be looking like this, but it's of course because the geothermal fluid has H2S, and H2S is and acids, and so then this can lead to acidification and impacts to the local area and fauna. So this gives you an example of how you can break up all these different components and essentially see like what role do they play in each one of these things, and for the ones that you're focused on, for example, global warming, how you can put in operational measures to combat this essentially. And then so Martha performed this LCI in 2012. Then she did it in 2017 for electricity and heat, different allocation methods, but essentially that you can see that because these operational changes, that it's led to around a 30% decrease in the greenhouse gas emissions coming from Hetlaseyði. And when you're thinking about in the spectrum of 50,000 tons of CO2 per year, now you're suddenly saving, maybe 15,000 tons of CO2 per year. And, that's quite a significant impact. So, and then this is now looking at LCIA, so not just for global warming, but also for all these different portions as well. And so how does this rank and compare? And this is usually you want to, like when you finish an LCA, one, as a realistic check for yourself, as well as to understand where does it fit within like kind of other studies of the same process. And then, but then of course for geothermal sites, it is quite important to consider that the geochemistry of the fluid is, can be quite different from sites where there's some geothermal sites, for example, in Turkey, which the emissions from those sites could be like almost like 1,000 grams of CO2 per kilowatt hour. And it mainly has to do with the composition of the rocks, where I think that it's limestone that's leading to it being like a very kind of CO2 and like potent geothermal fluid. And then when you're placing that within other technologies, I mean, if you look at like an industrial gas site versus hydropower versus geothermal, I mean, you'll see that hydropower and geothermal are all quite low. And I mean, of course, that the gas site is going to, blow it out of the water. But then, as I mentioned, when we're looking at acidification, geothermal is actually going to be, in this case, much worse because of the high H2S gas content of the gas, which is why Carbfix and Solfix was invested in to begin with. So the conclusions that you could take from this was that, direct emissions and the use of diesel fuel in drilling was like a major factor for the global warming potential. And then that we were able to reduce significantly the impact of emissions, I mean, both for the acidification as well as for global warming potential using Carbfix, and as well as greenhouse gas emissions associated with the drilling. And little can be done to minimize the use of steel because, of course, we're still going to need the pipes and we still need to include all of that. But, by decreasing the other emissions, you can gain as much as possible. So allocation, this is something that's still an ongoing discussion with no consensus for geothermal plants, but it is a work in progress. When you think about case studies, this is like a common research strategy in LCA studies, because of course you normally want to attribute this to one specific site. And case studies are usually attributional LCAs, which essentially mean that you're looking at one system and you're not thinking about this is maybe something I could have explained a bit more earlier, that there are attributional LCAs and then there are consequential LCAs. And so attributional are basically you're just attributing, looking at one specific process and trying to just suggest this is what the impact is of that process. And a consequential LCA, maybe that would be an example of Martha looking at LCA as it was, and then doing a consequential LCA of what if we did switch to electrical drilling within the process, and then that can show you what the switch are essentially. So, a case study approach has a strength, but it carries important limitations. You'll see here why. When you're doing a case study, it's a good approach to study like a well-defined process. And it enables rich analysis, and you're not overgeneralizing essentially. And the data availability is also often good, but it does not allow large-scale generalizations. Assuming that all geothermal plants would be exactly the same because you did let's say the case study isn't exactly applicable, like what I was talking about with the Turkish examples. And then because of the lack of generalization, it might be that findings could be too detailed for policy recommendations, even regarding the particular case. And so that's where, for example, in the EV paper where we reviewed 20 studies, rather than having one, just looking at one LCA study and suggesting that that's the truth, that's fact for everything. We looked across 20 studies and tried to create like a multi-case study essentially. So when you look at multiple case studies, so then you can enable comparisons and cross-case analysis, in our case, cross-study analysis. Then generalizations are possible with a high enough number of cases. Allows for theory building and theoretical sampling rather than random in-case selection. So that was the background on the geothermal plants. And I know this is kind of a lot of information coming fast. So again, if you have any questions, just feel free to jump in. I'll give you another example of LCA that I've done that I was working on for the Icelandic aluminum industry.
Can I just ask a short question regarding the headless Haiti power plant? First of all, thank you very much for this very extensive overview of the headless Haiti power plant case study. I have a question. You showed that about 30% of the carbon emissions are being re-injected and mineralized with the Carbfix project, right? Mm-hmm. Do you know, because our nature and also Reykjavik Energy would like to become carbon neutral, are there plans to increase the Carbfix to 100%, or do you know anything regarding the future plans of expanding Carbfix? My first question.
Definitely. I've been quite...
And maybe a follow-up question afterwards. obviously you need to re-inject the brine into the underground, and you probably need, I don't know, do you need to drill a new borehole if one borehole is used up? And does this again use diesel? And what is the carbon footprint of the re-injection process to put it back into the ground? Those two questions.
Okay, so I mean, I'll just take the first one, obviously. Yes, there's definitely plans to get to 100%. They have goals that by 2030, that On Power should be carbon neutral. So of course, like you're putting in a plant, so it's going to be like a stepwise growth, like, you know, maybe 3 years, and then they'll build the new, like while they're constructing like a new additional plant, and then it would be up probably towards 66%. And then 3 years later, they kind of plan to finish that, like, and have that last 100%, you know, kind of re-injected and using the Carbfix method. And as well as they're looking into utilizing CO2 within the geothermal park, was that if they could capture the CO2, and for example, there's algae innovation within the geothermal park, which is right in front of Hetlis City, and that if you could capture the CO2 and send that CO2 for algae production, then hopefully that could help lead a path towards, you know, carbon neutrality as well. And we're even discussing the possibility of going carbon negative, and especially because we have this Carbfix method of re-injecting the CO2 and turning it into stone. And Carbfix has now just become its own subsidiary. And Carbfix will hopefully now begin working, and they're now teaming up with Climeworks. If you're familiar with Climeworks, it's a Swiss direct air capture plant. And what they just made an agreement to, it's going to be called the Mammoth Project. And they've had a pilot Climeworks direct air capture unit at Hetlis City for quite some time, but it was not capturing very much, just maybe a few tons of CO2 per year. Now they're going to, like, you know, go 100x, and they're going to have a very large direct air capture plant sitting in Hetlis City in the geothermal park, using the electricity, the, you know, kind of clean electricity and clean heating that's there, and the Carbfix method to then basically capture CO2 directly from the air and re-inject it like directly into the earth and turn it to stone. And I mean, and this is going to be pretty like groundbreaking, that there's not that many places, you know, on earth. And this is a solution that if you look at like a lot of the IPCC kind of pathways towards how we can avoid 1.5 or 2 degree warming, many of them call for direct air capture and for, you know, basically negative emissions. And Carbfix, this Carbfix method and the ability to capture CO2 from the atmosphere are kind of like a key solution. And it's probably being, it might even be just the first time that this is really kind of happening at a full scale, you know, kind of commercial facility, and that hopefully they could then sell to companies who need to reduce their carbon footprint, that they could then, you know, purchase this carbon reduction, you know, from the atmosphere essentially. So that I find that to be pretty interesting. And then the second question was about the reinjection wells. Often it's not needed. I mean, of course, it has to do with the like kind of physics of the well. But most often they can reinsert a smaller tube within the same production well and then just send it right back down. But of course, there are other moments where they do need to include a reinjection well, like to reinject, and that's often like that's taken into account in Marta's work. Like she has LCI for the reinjection wells that were needed to be drilled like this. And for example, for Carbfix, you know, they might not need to, and often the reinjection wells, where in the production wells they go much deeper, they might be like 2,300 meters deep. The reinjection wells can be as low as like 600 meters deep. And for example, for Carbfix, they'll often only need to go to about 600 meters as opposed to 2,000 meters. So yeah, there's a little bit of, there's a different process, but yes. And also when you're thinking about like impacts of geothermal, this is maybe unrelated to LCA, but like maybe important when thinking about additional things you want to consider, is that reinjection often leads to induced seismicity. And a lot of that, like this is quite like a contention with stakeholders and a concern for On Power, and something that constantly needs to be monitored is, are they kind of inducing earthquakes to occur by reinjecting? And this is what you just want to be careful with, of course.
Thank you. I have a short follow-up question.
Sure.
I heard last time, I think this was a year ago, that the cost for the Carbfix project is about €20 for 1 ton carbon that is fixed and mineralized into stone. So currently the emission futures for carbon, at least for the European market, they're constantly going up. They're reaching almost €30. Is this a factor that plays into the strategy of Reykjavik Energy regarding going carbon neutral?
I think for the company's own carbon neutrality, maybe not so much. But in terms of Carbfix becoming a subsidiary, I think absolutely. I think it's moving out of a research and development into like a commercialized development where, I mean, it's looking to expand towards, I mean, here in Iceland, I mean, partnering, like there's been a memorandum of understanding with the Icelandic smelter, with the aluminum smelters, that like they could capture the CO2 from if they could capture the CO2 from their processes, that you could have a Carbfix site just next to the aluminum smelter, that it wouldn't have to be related to geothermal, and that you could just re-inject next to the aluminum smelter and help reduce those emissions. So like it's a business case that maybe wouldn't have existed without the issue of global warming. But of course, as global warming is becoming increasingly important, I think there certainly is an increasing role for a company such as Carbfix to re-inject and safely store carbon, essentially.
Thank you.
Yeah, no problem. And actually, speaking of Icelandic, a new aluminum industry, I'll just give you another quick example of a grant project that I had worked on. And this came like essentially as like my master's thesis, and looking at doing an LCA of the Icelandic aluminum industry, and with the implication of certificates of origin. So it's a grant project through Alcacene, basically doing an LCA of the aluminum industry to determine the friendliness of Icelandic aluminum production, in order to and this is another reason that companies do LCA, is that they can achieve, if they can publish an LCA, and then it shows that if their emissions are low enough, they can maybe get like a certification to suggest that, well, ours is cleaner, and it can either be sold as a green product, or it can help be a marketing factor to suggest that your product is cleaner. So an example of how, so it's just an example of this. And so this is suggesting the amount of renewable. So I took like a perspective on this that is of pretty high contention here in Iceland. It's basically that I'm sure some of you at least that have heard in the newspapers, and have I know that there's been some kind of documentaries and stuff about this, is that the guarantee of origin market here, which is quite a complicated system, that if anyone's ever suggested oh, well, on my bill it says there's nuclear power in Iceland, but anyone who knows Iceland knows that of course there is no nuclear facility, but there is a trading system which allows basically certificates to be traded, and the Icelandic energy companies have guaranteed that all businesses and homes and everything will get the guarantee of origins for free. That they will secure the fact that the energy that we are using from our houses are renewable. However, the smelters, this is not the case. The smelters are receiving zero guarantees of origin. So currently they are existing within the European market, where then it suggests that the smelters are using coal, gas, and all these different things. So and especially for an a very electrical intensive production process like aluminum, this is quite a big factor. Sorry, one moment. And then so you can see here, this is from Orkustofnan, and this is just from the newest reporting, but just that it was in 2016 that it suggested that there's 20% nuclear within the mix, 59% fuel, and only 21% of the certificates were kept for renewable energy. And so when you're looking at the LCA, you can see that it's estimated that 1 ton of aluminum requires 15,000 kilowatt hours. And if you think that the average US household over a year uses 11,000 kilowatt hours over the entire year, and in the US produced 850,000 tons of aluminum, I mean, you can see how that math is going to be a lot of electricity being used, and why it's important to think about where that electricity is coming from. So this gives you an example of the system boundary that when you're looking, and especially looking at an entire sector wide, is that you have the three major companies, Northern, Rio Tinto, and Alcoa, the transport of the bauxite, then you have the alumina refining, and this is just basically the process, and I guess I could have shown it more here, was essentially that first you have the bauxite. That bauxite is refined into aluminum, into alumina, and with the carbon anodes, like within the process that aluminum uses, and that's where the smelters are in Iceland, that you then make this, basically ton of aluminum using this kind of, kind of mass flow of how it works like this. So you have your aluminum production. You would then have the electricity mixed for each one of them according to who they're purchasing from. You have your geothermal and you have a hydroelectric. But then, this red is kind of showing the case of within the guarantee of origins, if you're including the emissions that are coming from the energy that's coming from these larger markets. So what I ended up finding out was that if you do kind of consider these emissions that come in, is that basically if you're using the Icelandic electricity mix, you're basically using basically the annual emissions of 70,000 Icelanders, and that's just because the process itself has emissions. But then if you imagine that they are using this European electricity mix, it becomes increasingly worse, and where it's basically that the tons, like the emissions that would go with each of these processes, basically put it above the level where they could be considered green aluminum. And so this is quite a point of contention. And I won't get too much into it. But it is a bit of a political debate. And I'll just frame it as such, is that the reason that this guarantee of origin market exists is because the European directive suggests that this would basically make renewables more profitable, thus enhancing the competitiveness of renewables. So every renewable provider should be allowed to sell this electricity to make their own operations kind of more profitable and to expand even more. The aluminum smelters suggest that they came to Iceland for cheap electricity and for green electricity, and that because this European market essentially turned on in 2014, now they have to pay more for what they had come here for. And I'm not going to get political, but that's just the kind of the debate that is ongoing. So that's just something to think about. And again, I know that we're kind of going across many studies here, but that's why I just want to show you kind of the use of LCA and all the different projects that are around it to kind of maybe pique interest. So I know I'm coming at you kind of with a lot of case studies and a lot of information. So
Kevin,
just
maybe
feel free to stop me.
a short question regarding the aluminum case study. You mentioned that the Carbfix project could also be applied to the aluminum sector. Is this possible? Because the aluminum smelters, they're located at different locations. Would it be possible to have a Carbfix project at those locations next to the aluminum smelter, so to capture the CO2 and immediately remineralize it? Do you know?
I think that. Yeah, I just think the geography at each one would need to be studied. But it's this basaltic rock that is basically underneath all of Iceland that allows the Carbfix process to work. And then if they could study the, kind of the geography of the area and then realize that it is a correct location, then yes, certainly it could be used. And that's the kind of explanation of Carbfix is the use of the basaltic rock. And so where Iceland is basically sitting only on basaltic rock, then yes, I think so.
I think Asbjørn Christiansen has a comment on this.
Yeah, I have one question too.
Yeah, sure.
I was just wondering about capturing carbon in the aluminium smelters. Do you have any technology for that?
I think certainly technology exists worldwide. I think that it's technology that is growing, but certainly there are carbon capture plants that, like in Sweden, are being applied to some of the steel industries there. Like I don't think Reykjavik Energy necessarily has the ability to do so, but aluminum smelters, I think it's always an issue of cost, is they probably could do it, but there's a large cost that would require for them to do it. So I think it could be. And I think as it becomes more kind of the pressure is increased to decrease the emissions from these industries, the more these technologies that will be implemented, and the more that they'll consider, like carbon solutions, and I think that's increasingly getting towards that point. Thus, why the Icelandic aluminum companies suggested that they would work with Carbfix if the opportunity is available. Was there
Asbjørn,
another question? Or
yeah, I think Asbjørn Christensen wanted to comment on this.
No, Asbjørn, we can't hear you. If you'd like, you can type your question in the chat and I can just read it out loud and then go on it.
Okay, maybe while Asbjørn is typing, I could ask a question. I happened to visit a carbon capturing facility in Germany. I think it was like 7 or 8 years ago. It's Schwarze Pumpe, and for some reason it never started up, and I got the impression that there was quite a lot of objections from the citizens living in the nearby neighborhood, and I don't know what was the major concern which they raised there, but somehow they didn't put that into production. They had all the facilities. It was I don't think it was a full scale, but it was sort of a half scale of the coal firing plant there, and then they were capturing the emissions from that, and they had everything in place except that they didn't get that boreholes and the solutions to inject it into the ground. Mm-hmm. So I don't know whether you have come across these solutions when you have done your research.
No, I mean I've read about them and been in I even actually been in a discussion and was going to go to Germany to see a site that's been developing like this. But in terms of why the social pushback would be there in that specific example, I don't really have too much feedback on that. But I think certainly, I mean, this is almost like a little bit of I don't know, not a space race, but there's many people who want to try to I think definitely we're on the new age of these solutions. And I think certainly, there's many companies and, countries interested in these type of projects. And I mean, why there would be social pushback against CO2, I'm not quite too sure, but that even if looking at hydrogen gas, and this is something me and David are going to be studying, is that there is a bit of a social pushback against H2 production, because many people consider it to be, and I mean it is I think a flammable or explosive gas, and so highly reactive gas, and so many people can be afraid of it. So that, and many people might then socially push back and suggest, well, I don't want a plant near me that might explode.
Right.
But then sometimes it's often reasonable, for example, but it's just something to think about, definitely.
Yeah, yeah.
And that's why taking stakeholders, like when doing these projects, like, you know, stakeholders should be taken into account, because if you try to apply the project without buy-in, you know, you might end up in a situation like this.
True. Okay, I think now you have the question there from
Yep.
Asbjørn.
It says, yeah, from Asbjørn, it's saying, would it be a benefit to use the, I'm not sure this word, incomes, or maybe just income for the certificate to help industries minimize their pollution? So yeah, definitely. And I think that's like essentially the point of giving the, I mean, of course, it's not giving the benefits to like a coal producing company, but say, especially for large companies, I know a lot of Norwegian companies and like Stat Oil and a lot of these like fossil fuel extractive companies, and also some of the like utility companies that are there, that instead of building like, you know, they had expertise in building platforms for oil drilling, now they're building platforms for windmills. So, and now by implementing windmills, they would start to get more money, you know, because of this process. Oh yeah, here in Iceland. I mean, sure. I mean, the certificates certainly are giving more money to Orkuvetan and more money to Landsvirkjun. And then Orkuvetan can then reinvest that money into Carbfix, for example, and now lead a new solution. And so certainly, and like we are participating in that certificate market. And OR is certainly, I mean, when you think about 80% of the electricity in Iceland is sold to like large scale energy users. So even if they suggest that, you know, 20% of the people, businesses, all of this, like are guaranteed, they're actually still selling 80% of what they're producing, and like, you know, selling these certificates and gaining income from it. And then they're using this to reinvest. So, I mean, I think it's definitely worthwhile. And then, you know, but, you know, it's quite a political issue. So I won't like commit too deep, but I mean, the setup of the whole institution is like this.
I would like just to comment on it. In the chat, I copy pasted the link to the current carbon emission futures. And you can see that the price actually multiplied 6 times over the last few years, from €5, from around €5 per ton carbon emitted to about roughly, it's I think €29 or 28, around 28, €29. So this shows that the market starts to work, that companies are actually competing for carbon certificates and are trying to reduce the carbon, because now it's not just an alibi exercise where you can buy cheap carbon emissions or cheap renewable energy from another company, because there's simply competition for it. And that leads to that leads also to a incentive to reduce the carbon emission for each company by itself, because simply if they would like to offset their carbon footprint by buying certificates, it will become very expensive. And that is simply a market that is starting to work towards solutions that become less polluting. So you can check this out maybe by looking at the development of the carbon pricing over the last few years in the link.
Mm-hmm. Exactly. All right. So I think we're getting near the end. This should be one of the last case studies. But this was the work behind my second PhD paper. And this is kind of like just another way that we use the LCA. And it's basically thinking about the second big debate and the importance of vehicle ownership, public transport, and travel behavior. And so it's kind of suggesting like, okay, I mean, like how this photo is showing, like this is what it looks like if I think it's 60 people are catching a bus, if they're all riding bikes, or if they're all in their cars. And not just looking at it in terms of like, I mean, you definitely have to think about it in terms of the street, how this affects the urban form of the city, where, I mean, would you need, if everyone were on buses like this, would you need such wide streets and parking and, you know, this more expensive networks? And for example, on bikes, but do you have the bike infrastructure to kind of support this modes of transportation? But then also to think about the life cycle emissions. So as we were showing, you know, whether it's an EV or a combustion vehicle, each of these have their production emissions. And then you multiply this by 60 in terms of the material that you need to produce this versus the material and energy to do this versus the material and energy to do this. And that's what many times urban planners and cities often, when they set a goal, like the city of Reykjavik has announced, okay, we're gonna have, they've suggested zero CO2 emissions by 2040 in the transport sector. Okay, great, but but it's zero in terms of direct emissions. And then if these are all EVs, these are all bikes, and then you just have this bus which is electric. I mean, all of those would have zero direct emissions. But what about the indirect emissions of producing all these vehicles and having a fleet turnover every single year of people buying new cars? And so this is something to think about. And then, so you could kind of map like, okay, but you want to think about the context of the city and how can it probably develop? So that's something here in Reykjavik, you know, this is kind of a car dominated, mature city. It's already kind of established in its structure and urban form. So how can you really improve it? I mean, you can try to encourage more walking and movement, more transportation, new mobility services is like a big factor. And then that you could possibly casually decrease the role of car ownership, but possibly not as much as you could in a mega city or an advanced city where, you know, you can apply other options more easily. So the way that we kind of modeled this was doing a story and simulation approach. So we created some scenarios that like really developed, trying to create an approach in which we look at scenarios of if this happens or if this happens, you know, what would that look like? And then try to simulate it through a model and then suggest what this would, what the city would look like. I'm not going to dig too much into this, but if people are interested, it's not really LCA exact. There's some LCA portion to it, and I'll just describe it quickly. Is the greenhouse gas emissions related to a transport sector? Is basically you look at the population of the place that you're in. How much does that population want to travel per day? How much are they traveling? And then basically like a utility factor in terms of bus, are you having 20 people in a bus or 10 people in the bus? And if you're driving individual cars, I mean, does everyone drive their own car, or do you hop in the car with your parents and, you know, they take you where you need to go, for example? Then you have the fleet composition. So this is the important factor when you're starting to look at production emissions, and I'll explain that in a second. So, I mean, what's the percentage of electric vehicles within the car fleet? Like when we showed Norway being at 50% and Iceland being at 15%, what is the fleet made of? And what is the emission factor for each one of these vehicles? And that's including per vehicle type. So, I mean, emission factor for a bus, but also the emission factor for your diesel car, for your petrol car, for your EV. And then, so you're looking at the direct, you know, emissions, but then you also want to look at the indirect emissions, which, often cities will just cut the line here and only look at this, but they don't look at the indirect emissions of vehicle purchases, of vehicle disposals, of production emissions, and disposal emissions. And this was this paper just got published in an academic journal, and one of the defining features of it was that we took these life cycle emissions that we took from the 20 study LCA that we did and applied that work into the transport sector and thought about okay, well, now if you're constantly, that was just for one vehicle, what happens now at a fleet level? And that's what we wanted to look at. And I'm only going to mention this because it's interesting, but there's basically three main actions that you can do, and you can basically just try to avoid travel demand or avoid purchasing vehicles or disposals. You can shift to public transport or kind of different mobility options, or you can improve the system that you're working in. For example, replacing electric vehicles, the bus fleet to electric buses, an example for things like this, and trying to reduce these emissions and improve, for example, the production. If we get better and better at producing vehicles, their impact will be less and less. So those are kind of like the three options that you have to reduce kind of the emissions associated with the transport sector. So the way we did is we kind of developed scenarios that we looked at. We have our business as usual scenario, and we did like a 2-axis development. So basically on one side, we just went up and suggested, okay, if you just look at urban structural form and lifestyle choices, if you improve the bus system and urban densification, walking and cycling, you didn't think about so much about like EVs and electrification, but just like if we make the city more efficient, would it be better? Or, okay, let's not even worry about densifying. Let's not worry about do these other things, but let's just go straight EVs and just go for it. And how would that end up? And then, you know, an approach of taking both of these, and then if you radically change and take a massive support for carless lifestyles and reduction of travel demand. And I'll show you, these are kind of like some of the defining variables of them. So like modal share, right now in Reykjavik, around 90% of people travel by personal vehicle. So we're suggesting in the radical change that by 2050, you know, this would plummet. And then obviously in like the land use change, this would be less, you know, and looking at these type of things, vehicles per 1,000 inhabitants, Iceland is always competing in number 1 or number 2 of highest car ownership in all of Europe. And then, so is that trend going to continue into 2050, or will be there a major push to suggest I don't need a car? The downtown becomes more densified. The bus system with Borgarlina, these type of things don't require you to need a vehicle. Like, would this change over time if the government supported policies to do that? Electrification rates, how many EVs are going to be filling society? And then travel demand per capita, like if the city is more dense, do you need to travel from Hafnarfjörður to downtown? Or if you just live downtown because of this higher densification, would you then be needing less travel demand, you know, per day, essentially? So the way that this looked was that you can see the annual greenhouse gas emissions per the scenarios. So in this radical change, it dropped much more. And then you can see that in the tech scenario and in the urban form change scenario, that it resulted in like close to the same final emissions. But I'm going to show you why that's interesting, why this relates to the LCA lecture. Essentially that in terms of direct greenhouse gas emissions, like we saw for like EVs don't really have a direct greenhouse gas emissions. And it was suggested that by 2050, everything would be electric. Well, then you pretty much have 0 greenhouse gas emissions. Now, the thing is, then you look at the indirect greenhouse gas emissions, like what would it take, how many vehicles would constantly need to be produced to fulfill high vehicle ownership, and if you want them all to be EVs, and you basically have to change your entire fleet over, well, the indirect emissions are going to be quite high. Where in the tech scenario, it's even worse than like the worst case scenario that we modeled because you have so many EVs with this higher production emissions. And then you can see in the urban structural change, the indirect emissions pretty much just stay flat. And so you're kind of seeing that like cumulatively over the entire time period, like the tech scenario ends up worse off than the urban structural change and lifestyle change because this indirect emissions is just so much higher. And then so that kind of puts like why life cycle thinking is important, that it's not just about the direct greenhouse gas emission, but also should we be owning all these vehicles and changing everything over? And then you can kind of just see it here, like what the drivers of that are. And we did a decomposition that essentially suggesting like, you know, technology would lead to the greatest, you know, kind of win in emissions. But at the end of the day, like the car fleet will also lead to a lot of emissions if we don't like put a kind of cap on levels of car ownership or not try to reduce it. And from a policy perspective, this is interesting because the city of Reykjavik's climate policy is suggesting that by 2040, emissions from automotive traffic and public transport will be 0. But then even in our model, like even in the most radical change that we took, where we suggested, you know, only 10% of trips would be like, you know, with personal transport and rapid electrification, only in the radical change scenario did that become true. So one, you know, it kind of suggests that maybe they're putting a goal without really thinking about how they're going to get there. And then 2, that it doesn't mention car ownership at all. So when you think about like the indirect emissions, you know, that there's a huge amount of indirect emissions that are kind of being ignored by not talking about vehicle ownership and about its role like in dealing with direct and indirect emissions. So we're pretty much just going to wrap up here. And then, you know, maybe David can jump into this more if he's interested. But now this is some of the future work that David and I are going to be going into. And it's looking at the hydrogen production LCA, and it's asking basically, how is green hydrogen produced? And what we're going to look at is what do the markets look like? I mean, you have hydro and wind should be, and solar, and we're going to look at these different ways and also connected to the geothermal plant. How is hydrogen being produced? Basically, probably most of it will be done through an electrolyzed process where you add water, you do this electrolysis, and then you create this hydrogen, which could be used as a fuel. And then you store this hydrogen. And then this is like the questions that we're going to be asking is it best to produce it here in Iceland and ship it to Europe? How should it be used? Should it be used within the electrical sector or for vehicles or, for what, like industrial use, domestic use? How will it be used and how will it be made? And then looking at the environmental impacts of it. And as we talked about, also doing a stakeholder analysis. And so this is the work that we're getting into. And David, I mean, maybe you can touch a bit on it, like, and discuss interest in the project. And that,
Yeah, I can very shortly comment on this. This is a project that we just started a few months ago. So we're in the process of setting it all up. But obviously it's always possible to embed a master's thesis or a student project within one of these projects. So if you're interested, just contact me and Kevin, and then we'll see, depending on your background, how you could contribute to this project. And obviously, as you might have realized, this is really a emerging topic. So there will be probably other projects that will come up in the beginning next year. I also mentioned it at the beginning of this course. We have a strong collaboration with the University of Linz in Austria, where they do a lot of LCAs, and also with Switzerland, where they have the EcoInvent, the company, the database where all the LCA data is stored. So there are options also to do an internship at one of our partner universities to learn how to use the LCA databases and to learn from other experiences as well. So there's a lot going on in that sector. So if you're interested to get involved in this, then feel free to contact us, and we'll see how we can set this up. If there are any questions, please feel free to post them or just open your microphone and ask them right away.
Yeah, and just let me know if there's any last questions. If I can wait for 1 minute, and if not, then I'll just tell you all thank you for listening and enjoy your week.
I actually have one question.
Yeah, sure.
Do you have like a good place to start if you're sort of trying to do comparative life cycle assessments, for example, regarding to agriculture? Is there like a main database that, someone who doesn't have any licenses could use, or is it just, trying to find scientific papers?
No, I could recommend that you go to Open LCA, and they have a website, and it's also like it's an open source software where you can do an LCA now, where some of these softwares can be quite expensive, Gabi and stuff like this, but Open LCA is open source. You can download that for free. And this is just like the structural program that allows you to run an LCA. But then on the databases, you can go to like their website, and they'll have a list of databases that are free or that are paid for. And definitely a good place to start. And I think they have one focused on agriculture that you could take a look at. But maybe not everything has like maybe, databases can always be limited just essentially by what's in there. And then if you do find that, well, then you should start maybe trying to find a process that's similar. Because if you're looking at vertical farming, perhaps they don't necessarily have, a very specific thing on vertical farming. And then maybe that's where then you start developing kind of your own process, and then you can maybe compare it to, like 1 kilo of lettuce produced in Spain or something, and they might have all the impacts related to that. But then if you're doing 1 kilo of lettuce produced in vertical farming or something, then you can, do those comparisons essentially.
Well, you actually hit the nail on the head, because that's exactly what we're doing for this course.
Yeah,
we're going into
exactly.
Vertical farming, and I was just wanted to get the comparison, to get something to compare with.
Yeah, but if you're in contact with VAXA, then you could probably like ask a question about like getting information about their electricity use, about their heat use. It might, in a short time period, it might be difficult to get like every single material component essentially of like, you know, like the stacks that they have and stuff like this. But in terms of water use, electricity use, heating use, I mean, that's like basically a great start. And then you can, I mean, depending on the time you have and the ability to collect the data of like getting material use, but because you know that the inputs, like the inputs are going to be most important essentially in terms of like when you're doing LCA, like, you know, you definitely want to grab those and then work to your like less important data. And I think that water use, you know, like what I just mentioned are going to be the key ones. And then look at like the life cycle emissions that are going to be coming from each of those products that are coming in, and you're going to be kind of like on your way essentially.
Okay. Would you recommend to take in the sort of biochemical aspect as well, and because they're probably going to do some sort of like nutrient solutions compared to conventional fertilizer then for the comparative, for example, like conventionally grown lettuce?
Yeah, sure. I mean, definitely all the chemicals used, you can definitely like can and should include those as much as possible.
Yeah. Okay. Thanks. You answered more than a question for me. Thanks. Super.
Yeah, no problem.
Okay, if there are no more questions, then I would like to thank Kevin. Maybe we can give him a virtual applause. It's unfortunately not possible to give you a real applause, but you can click the little clapping icon. And Kevin, thank you very much for joining us. Of course, you will be around during the next 2 years on the project on the hydrogen project, and yeah, we look forward to future collaborations. And thank you, everyone. We will meet tomorrow again. Tomorrow we will start with the Finnish case studies, and we will meet tomorrow same time again for the next case studies. Thank you very much, everyone.
Yes.
Yeah, maybe there's some questions also.
Sorry.
Yeah. Go ahead.
Sorry.
The floor is yours. Sorry.
Sorry. Okay. Thank you, David, and thank you, everyone, for listening. So tomorrow, Pentti Viloksela will give you a lecture and some background on basic sustainable development and especially sustainable cities. And as David said, we will start at 10 o'clock Iceland time and 12 o'clock here in Helsinki time. So meet you all together tomorrow again. Thank you from my side as well.
Thank you, everyone. Have a nice afternoon. See you.
Thank you, everyone.
Bye.